The production journey starts with planning and design, where a team of experienced engineers and product designers utilize advanced CAD and FEA tools to model a wide range of wheel styles. Sizes vary from 12 to 22 inches, accommodating different vehicle types and customer preferences. Once approved, the design enters the foundry phase. At this stage, high-purity aluminum alloy is melted and poured using robotic gravity die casting or low-pressure die casting (LPDC) systems. Robotic handling ensures uniformity, reduces human error, and eliminates casting turbulence, resulting in stronger, denser components. Every batch of molten alloy is subjected to spectroanalysis to verify chemical composition, followed by metal density tests to identify structural consistency. After casting, wheels are degated to remove excess metal, then undergo X-ray scanning to detect internal porosity or hidden defects. Neo Wheels has been a pioneer in the Indian alloy wheel industry since its inception in 1996. As the country's only RI-certified alloy wheel manufacturer, Neo Wheels has built a reputation grounded in safety, structural strength, innovation, and aesthetic finesse. With a distribution network of over 100 authorized dealers and more than 2,000 selling points nationwide, the company ensures seamless access to high-quality alloy wheels for customers across India. Next comes heat treatment, a multi-step thermal process that includes solution treatment, quenching, and artificial aging. These procedures significantly improve the wheel's tensile strength, ductility, and fatigue resistance. After heat treatment, each wheel is subjected to tensile strength testing using calibrated equipment to confirm mechanical reliability under heavy loads and extended usage. These wheels are not just built for performance, they're engineered for endurance and refined through years of craftsmanship and constant technological upgrades. The wheels undergo leak testing to ensure airtight integrity, and then proceed to run out and dynamic balancing checks, crucial for maintaining smooth, vibration-free motion. A dimensional inspection is also carried out to ensure the final geometry matches the CAD blueprint within acceptable tolerance limits. The wheels then move into the precision machining phase. In the CNC-controlled machine shop, each wheel receives a unique identification stamp for traceability. Lug holes are drilled with micron-level accuracy to ensure proper fitment on a variety of vehicle hubs. The digital models undergo intense simulation testing, including stress analysis and weight distribution studies, ensuring that every design can withstand real-world forces, such as cornering loads and road impacts. Following machining, wheels enter the finishing operations stage. This includes surface pre-treatment for degreasing and cleaning, followed by pre-paint inspections to detect any surface imperfections. Powder coating is applied for enhanced corrosion resistance, and paint thickness is carefully measured to ensure uniform application. Select models undergo diamond cut machining to create signature two-tone finishes, and a final clear coat provides UV protection and a high-gloss finish. To validate corrosion resistance, samples are subjected to salt spray testing, simulating years of harsh environmental exposure. Before packaging, each wheel undergoes statutory testing, including the cornering fatigue test (CFT), radial fatigue test (RFT), and the impact test. These ensure that wheels can endure side loads, vertical forces, and shock impacts like potholes or sudden curb hits. Only wheels that pass every quality checkpoint are packed and shipped, ensuring consistent safety and reliability for end users. Through an optimized blend of automation, human expertise, and rigorous testing, Neo Wheels has set the gold standard for alloy wheel manufacturing in India, delivering products that are durable, elegant, and performance-ready. Michelin's retreading process is a highly controlled, 9-step method engineered to extend the life of commercial tire casings while maintaining performance and safety standards equivalent to new tires. The process begins with initial inspection, where trained technicians assess each casing for visible damage and determine its suitability for retreading. In buffing, a computer-controlled machine removes worn tread to a uniform profile and texture. This is followed by chirography, a laser-based inspection detecting internal issues such as belt separations. If necessary, X-ray scanning is used to analyze the steel belt structure for hidden defects. This precise retreading process reduces tire waste, saves up to 70% of raw materials, and cuts costs by nearly 40% compared to new tire replacement, making it a key component of Michelin's sustainable mobility mission. In the repairing stage, cuts and holes are patched using uncured rubber and black cement. These areas are pressure cured to restore casing integrity. Next, the tread building phase involves applying a pre-molded tread using hot cushion gum, ensuring high-strength adhesion. During enveloping, the tire is sealed in dual layers to create a vacuum environment for uniform curing. The curing phase occurs inside a computer-controlled chamber, where heat and pressure bond the new tread permanently to the casing. Finally, the final inspection includes checks on the tread, sidewall, bead, and interior. Only tires that pass Michelin's stringent quality standards are released for service. Changing a main landing gear tire on the Airbus A321 involves lifting the aircraft with a 60-ton hydraulic jack, removing 8 to 10 nuts with a torque-controlled impact wrench, and replacing a 110 to 120 kilograms wheel. The new tire, pre-inflated to 200 to 220 psi with dry nitrogen, is torqued to 220 to 250 pound-feet. Digital gauges ensure pressure accuracy within plus or minus 0.5 psi. Final checks include brake wear, tire runout, and logbook documentation per EASA Part 145 standards. Each wheel change typically takes 45 to 60 minutes, and dual tire replacement is recommended if a flat has occurred, due to uneven load distribution. The Boeing 787 Dreamliner is built with 50% composite materials and assembled in 35 to 50 days. Major components: wings, 60.1 meters, fuselage sections, stabilizers, are produced globally and flown to Everett or South Carolina by Dreamlifter cargo jets. Robotic systems and automated fiber placement machines ensure precision. With a $1 billion investment and 7,000-plus staff, the 787 achieves 20% better fuel efficiency than previous aircraft, like the 767. Wood Group Pratt & Whitney, WGPW, a division of Ethos Energy, delivers comprehensive industrial turbine services for Pratt & Whitney GG4 and FT4 Aero-derivative gas turbines, typically rated between 20 and 30 megawatts. Based in a 6,000 square meter facility in Bloomfield, Connecticut, WGPW employs over 100 skilled engineers and technicians and is equipped with advanced tools, including CNC machines with plus or minus 0.002 mm tolerance, 25-ton overhead cranes, and a full-speed test cell capable of operating turbines at 7,700 revolutions per minute under simulated load conditions. The overhaul process begins with complete disassembly of engine modules, followed by non-destructive testing methods such as ultrasonic inspection, dye-penetrant testing, and eddy current scanning. Hot section components like turbine blades, vanes, and combustion liners are refurbished using plasma arc welding, thermal barrier coatings, and precision remachining to meet OEM specifications. Rotor assemblies are dynamically balanced to ISO grade G 2.5, ensuring vibration levels remain under 1.5 mm per second RMS during operation. After reassembly, each turbine undergoes full load performance testing to validate output, exhaust temperature, emissions, and efficiency. WGPW services more than 100 turbine units annually, with typical turnaround times ranging from 90 to 120 days. Each service turbine is delivered with AS9100 compliant documentation, FAA traceability when required, and is certified for up to 25,000 additional operational hours, ensuring long-term reliability and performance in demanding industrial environments. The China Airlines Boeing 777, the world's first co-branded livery between Boeing and an airline, was meticulously assembled at the Boeing Everett factory in Washington, the largest building in the world by volume, 13.3 million cubic meters. This aircraft's production spanned 49 calendar days, involving a blend of high-precision machinery and human expertise. Key aircraft components were manufactured globally: the forward fuselage by Kawasaki Heavy Industries, center fuselage by Fuji Heavy Industries, and the wings, spanning 64.8 meters, in Nagoya, Japan. These parts were transported via Boeing's Dreamlifter cargo aircraft to Everett for integration. Each of the GE90 engines, rated at 512 kilonewtons, 115,300 lbf of thrust, was installed using automated handling rigs and laser-guided jigs. The moving assembly line advanced at 4.2 meters per hour across 20 stations, where different modules were integrated: fuselage join, wing body join, vertical fin, and horizontal stabilizer installation, followed by complex system integrations. The aircraft includes over 250 kilometers of electrical wiring and around 6,000 fasteners for hydraulics, avionics, and air systems. Interior installation involved seating for up to 396 passengers and full galley setups. A special painting process took up to 5 days, using more than 200 liters of paint, combining hand-masked art and precision vinyl decals. After multiple ground tests and a 4-hour test flight, the aircraft was certified for delivery. Building a liquefied natural gas (LNG) carrier is a highly complex process involving thousands of engineers, technicians, and advanced machinery across facilities covering over 300,000 square meters. The process begins with a detailed design phase lasting 12 to 18 months, using software like AutoCAD, CATIA, and Aviva Marine. Over 100 engineers collaborate to develop 3D models and technical drawings. Hull assembly alone takes 6 to 8 months. Once the hull is complete, installation of cryogenic cargo tanks begins. Each LNG tank can hold between 125,000 and 266,000 cubic meters and is made from 9% nickel steel to withstand -162 degrees Celsius. Insulation is provided via polyurethane foam or perlite. Next, the ship's complex piping, pumping, and automation systems are installed over 3 to 5 months. These include centrifugal pumps, rated at 1,500 cubic meters per hour, and SCADA-based control systems. All installations undergo rigorous non-destructive testing, ultrasound, radiography, and magnetic particle inspections. Pressure tests follow, with tanks subjected to 1.5x working pressure and cryogenic testing at -162°C to ensure structural integrity. The vessel is then coated with 200 to 300 micron epoxy or polyurethane paint for corrosion protection. After final checks, the ship is launched using a floating dock or inclined slipway. Sea trials, testing propulsion, control systems, and LNG handling last 1 to 2 months before final delivery. The full build cycle spans 24 to 36 months. At Cima Callao, one of Peru's most advanced naval industrial facilities, Naviera Petrol's chemical tanker Moquegua undergoes its scheduled dry docking for a comprehensive biennial maintenance program. The process begins early in the morning with the controlled opening of the dock gate and careful maneuvering of the vessel into the floating dock. Once in position, the ship is stabilized on keel blocks to ensure safe access to all underwater components. A critical first step involves high-pressure water blasting to remove marine growth and biofouling, which negatively affect fuel efficiency and hull performance. Following this, the hull is subjected to abrasive blasting with copper slag to remove old coatings and surface impurities, preparing the steel for repainting. Simultaneous to the hull work, engineering crews dismantle the vessel's entire propulsion shaft system, removing, polishing, and inspecting the propeller blades, checking shaft alignment, and reinstalling flanges and shaft seals. Hydraulic systems, crucial for operating ballast and cargo pumps, are also cleaned and maintained to ensure operational reliability. Inside the vessel, special attention is given to its 316L stainless steel chemical tanks, which are used for transporting sulfuric acid. Tank interiors are meticulously inspected for corrosion, pitting, or wear, ensuring full compliance with safety and quality standards. The vessel then undergoes a 4-coat painting system, with the final layer being a silicone-based anti-fouling paint that meets modern environmental regulations and significantly reduces the adhesion of marine organisms. This enhances long-term hydrodynamic performance. All work is executed under strict project management, with simultaneous operations coordinated to meet the scheduled refloat date. Once inspections and coatings are completed, the dock is carefully flooded, and the vessel is floated out, ready for deployment. Naviera Petrol, a Peruvian leader in maritime chemical transport, ensures its fleet remains in optimal condition year-round through rigorous maintenance, engineering excellence, and adherence to global standards, delivering safe, efficient, and environmentally responsible service to its clients. The Hansa Australia is a 3,649 TEU container ship measuring 239.5 meters in length and 32.2 meters in width. Built in 2014 at Shanghai Shipyard, it features a double-hull design and is powered by a MAN K80 engine, producing 27,180 kilowatts. Its propulsion system includes a 50-ton fixed-pitch propeller manufactured by MMG in Germany. The vessel operates under the Marshall Islands flag. The Atlantis J7 is a modern recreation of a Super J yacht designed by renowned American naval architect Frank C. Payne from the 1930s. The original lines plan, known as the Design A, was never built until now. The project began with a 6-month effort to digitally reconstruct the original drawings. Naval architects scanned the 1930s blueprints and created high-resolution 3D CAD models, refining the geometry to comply with modern safety, structural, and performance standards. The J-Class Association requires all yachts to fall within specific parameters, such as waterline length, 26.5 meters max, and sail area. Every curve and line of the hull was digitally modeled to tolerances within plus or minus 1 millimeter. Hull construction and materials. Atlantis measures approximately 42.5 meters, 139.4 feet, in length overall, with a beam of 6.6 meters, 21.7 feet, and a draft of 4.6 meters, 15 feet. The hull is constructed entirely from marine-grade aluminum alloy 5083H116, favored for its strength-to-weight ratio, corrosion resistance, and weldability. Fabrication took place in a specialized facility, equipped with 5-axis CNC plasma cutting machines, automated rolling systems, and climate-controlled clean rooms for welding. Over 150 individual hull plates and stringers were laser-cut and precision-welded, using MIG techniques. The hull was then faired and coated with epoxy-based barrier coatings to ensure long-term durability and racing performance. Mast, rigging, and sail plan. The yacht's mast stands 53 meters, 174 feet tall, constructed from high-modulus carbon fiber in an autoclave for maximum stiffness and minimal weight. The boom and spinnaker pole are also carbon composite, with titanium fittings. Atlantis carries more than 1,000 square meters, 10,764 square feet, of upwind sail area, including a mainsail, genoa, and staysail, made from 3-dye composite sailcloth. A hydraulic forestay system applies up to 35 metric tons of tension, providing precise mast rake and headstay control. Interior and systems integration. Despite its classic exterior, the yacht features fully modern systems, navigation suite, B&GH 5000 instruments, GPS, AIS, and radar. Hydraulics, Lumar Race Series winches, digital load monitoring, power, twin 100 kilowatts generators, and 48 volts DC lithium-ion battery system. HVAC and fresh water. Climate control with zoned ventilation and water makers, producing up to 120 liters per hour. Launch, trials, and legacy. Atlantis was launched in 2023 after 36 months of construction. She is fully Lloyd's Register certified and eligible to race in official J-Class regattas, including the America's Cup Superyacht program. As a unique blend of historic design and advanced engineering, Atlantis stands as a floating masterpiece, reviving a yacht once imagined but never realized. The restoration of the classic sailing yacht Cassiopeia is a monumental feat of traditional craftsmanship, engineering expertise, and dedication. Built with a triple-layer planking of Iroko and mahogany over oak frames, Cassiopeia is not just a vessel, but a living legacy of naval architecture. Her full restoration process spanned over a decade and involved an incredible level of detail, with work carried out by a seasoned team of artisans and shipwrights. Initial survey and restoration planning. The process began with a thorough structural and surface inspection. Each plank of the hull was meticulously examined to determine its condition. Due to the age of the boat, many of the ribs were over 60 years old, requiring careful replacement or reinforcement. This inspection phase led to the development of a multi-phase restoration plan, covering structural work, system upgrades, and aesthetic refinishing. A team of naval engineers and restoration experts collaborated to map out a detailed restoration schedule, budget, and materials list. The timeline was expected to span several years, with milestones reviewed quarterly to ensure progress stayed aligned with project goals. Full dismantling and storage. Once planning was complete, the dismantling phase began. All masts, booms, deck hardware, and removable components were carefully removed and catalogued. The mast and boom were taken down in 2023, stripped, inspected, refinished, and reinstalled in May 2024. Each element was labeled and stored in climate-controlled environments to prevent moisture-related damage and material warping. This careful disassembly ensured that each component could later be reassembled precisely, while allowing full access to the hull for structural and cosmetic work. Structural restoration of the wooden hull. One of the most challenging phases of the project was the structural refurbishment of the hull. Cassiopeia's hull, originally built using a cold-molded method with triple planking, Iroko and mahogany, was in need of extensive replacement work. Over a 10-year period, every plank on the hull was either restored or replaced. Craftsmen used traditional hand tools, chisels, planes, adzes, as well as specialized modern equipment like bandsaws, sanding stations, and industrial clamps. In total, hundreds of meters of hardwood were shaped and steamed to match the curvature of the hull. Shipwrights often had to custom build their own tools to tackle unique restoration challenges. Working without pre-made templates, they relied on generational knowledge and an intimate understanding of wood behavior. Each plank was treated and fitted by hand, with discussions between craftsmen happening on the spot to adapt to the needs of the wood. Mechanical and technical overhaul. As the wooden structure neared completion, the focus shifted to internal systems. All technical equipment aboard Cassiopeia underwent full disassembly and inspection. The main engine, generators, plumbing systems, and electrical infrastructure were modernized to meet 2024 standards while preserving the yacht's historical aesthetic. This phase involved updating all hydraulic lines and cabling, installing energy-efficient pumps, and introducing modern navigational and safety equipment. Though modern equipment was installed, care was taken to ensure it blended with the original character of the vessel. This process took approximately 4 to 5 months and involved a team of electricians, marine engineers, and automation specialists. Surfaces were sanded multiple times between coats to ensure perfect adhesion and finish quality. This stage took 4 weeks, including drying and polishing periods. Reassembly and sea testing. Following completion of the hull and systems, the reassembly phase began. All deck fittings, masts, and interior features were reinstalled. The yacht underwent extensive sea trials to test handling, propulsion, and system integration. These trials lasted between 1 and 2 weeks, during which minor adjustments were made to rigging tension, engine tuning, and electrical loads. Hydrostatic testing confirmed the yacht's balance and water tightness, while crew training sessions ensured operational familiarity with updated systems. Legacy and cultural significance. Cassiopeia's restoration is not merely a technical project, it's a cultural mission. The artisans involved in the restoration began their careers as teenagers, some as early as age 10, learning under old masters. Many of them have worked together for over 45 years. For them, craftsmanship is second nature. As they say, if we don't go home covered in sawdust, we haven't done anything. Exterior refinishing and painting. By early 2024, the hull was ready for finishing. In April 2024, the entire hull received a new coating of marine-grade varnish and protective paint. The finishing included multiple layers of epoxy-based primer, followed by traditional yacht enamel, with a combined thickness of 200 to 300 microns to provide UV and saltwater resistance. The production process begins with computer-aided design (CAD), followed by CNC cutting of 12 to 25 mm thick HDPE sheets to exact dimensions. Hull components are then joined using extrusion welding and butt fusion welding, ensuring long-term seam integrity. Unlike fiberglass or aluminum, HDPE hulls are assembled without rivets or bolts, significantly reducing failure points under mechanical stress. Each hull is equipped with sealed PE buoyancy chambers and reinforced lifting eyes to support demanding operations. HDPE's density of 0.93 to 0.97 grams per cc makes it lighter than water, enhancing buoyancy and fuel efficiency. The material is also UV stabilized, corrosion-free, and resistant to marine growth, which eliminates the need for bottom paint, cutting down both maintenance time and environmental impact. Turbine Boats emphasizes environmental responsibility. HDPE is 100% recyclable, and production waste is minimized through efficient material nesting. The hulls are tested for impact durability, often withstanding direct hits from sledgehammers without structural compromise. With rugged design, low lifecycle costs, and minimal maintenance, Turbine HDPE hulls offer a sustainable, tough, and long-lasting solution for modern marine operations. Turbine Boats US, with over 35 years of experience in plastic fabrication, manufactures high-performance hulls using high-density polyethylene HDPE at facilities in Massachusetts, Wisconsin, and Florida. The company produces both standard and custom hull designs ranging from 14 to 40 feet in length, specifically tailored for workboats and high-impact marine environments. Trailing suction hopper dredgers, TSHDs, are ocean-going vessels designed for dredging and transporting large volumes of seabed material, such as sand, silt, and clay. These vessels are essential for port construction, maintenance, land reclamation, coastal defense, and riverbank protection. A TSHD operates by sailing to the designated dredging area and lowering one or two suction pipes, each equipped with a draghead. As the vessel moves forward at a reduced speed, typically between 1 and 2 knots, the dragheads loosen the seabed material. Powerful dredge pumps then suction the material through the 1,000 to 1,200 mm diameter suction pipes into the onboard hopper. A typical hopper, like that of the Barnacles TSHD Queen of the Netherlands, holds up to 35,500 cubic meters of dredged material and can dredge depths of up to 160 meters. Once the hopper is full, the vessel proceeds to the discharge area, where the dredged material is unloaded using one of several methods depending on the project requirements. Bottom dumping is performed by opening hopper doors located beneath the vessel to release the load directly to the seabed. In rainbowing, sand is sprayed in a high arc through a nozzle at the vessel's bow, typically used when the vessel can approach close to the shoreline. Alternatively, the pump-ashore method employs floating or submerged pipelines to transport the material directly to land reclamation zones or coastal protection sites. The vessel's precise positioning via GPS and dynamic tracking ensures accurate discharge, minimizing environmental impact, and optimizing fill quality. Modern TSHDs operate with installed power exceeding 27,000 kilowatts, enabling efficient and continuous operation worldwide. Barnacles and other dredging contractors use these state-of-the-art vessels to support infrastructure development and coastal resilience across the globe. In June, the 44,000 DWT bulk carrier MV Bonita, 181 meters OA, 30 meters beam, ran aground off Mauritius. Over 40 days, a major salvage operation was executed. Over 230 cubic meters of contaminated oil was airlifted using helicopters across 750 flights, totaling 157 flight hours. To restore buoyancy, salvers pressurized cargo holds with 4,200 cubic meters per hour of air via 3.5 kilometers of hoses, sealed by 5 kilometers of welding. 30 submersible pumps powered by 1 megawatt generators removed water at 4,000 cubic meters per hour. More than 2 kilometers of Dyneema tow lines were used to refloat the vessel. The team included 3 salvage masters, 20 welders, 8 divers, and over 100 personnel. On July 27, the ship was freed by tugs Ionian Seafoss and Coral Seafoss. The successful salvage highlighted precision engineering, logistics coordination, and environmental protection in one of the Indian Ocean's most complex marine recoveries. Dry docking is an essential process in the maritime industry, allowing vessels to undergo structural maintenance, hull inspections, and critical system overhauls that cannot be performed while afloat. Depending on a vessel's type and regulatory requirements, dry docking typically occurs every 2.5 to 5 years and lasts between 7 and 30 days. Once dry, the hull is cleaned using high-pressure water jets up to 2,500 bars, removing biofouling and old coatings across an area that can exceed 10,000 square meters. Non-destructive testing methods like ultrasonic thickness measurements and magnetic particle inspection identify structural degradation. If hull steel is reduced by more than 25%, replacement is mandatory. When the ship arrives, it is maneuvered into the dock using tugboats and aligned precisely over pre-positioned keel blocks. Once secured, the dock's pumps, capable of discharging over 10,000 cubic meters of water per hour, are activated. Dewatering the dock can take 8 to 12 hours depending on its size. Divers confirm correct hull positioning during the final stages. Preparations also involve generating a repair list, safety documentation, and allocating resources. A repair crew for a medium-sized vessel can include 30 to 80 workers, covering welders, painters, engineers, electricians, and divers. The operation begins with detailed planning. A dry dock project team develops a docking plan that includes the vessel's dimensions, weight distribution, and keel block layout. Mechanical systems are then overhauled. Main engines, usually serviced after every 10,000 operating hours, are inspected, along with propulsion shafts, rudder gear, ballast valves, and fire suppression lines. Electrical circuits are tested for continuity and insulation resistance. Finally, the hull is coated with 300 to 400 microns of epoxy primer, followed by anti-fouling paint to prevent marine growth. After successful pressure tests, functional checks, and recertification from a classification society, the dock is reflooded and the ship is towed out, restored, upgraded, and ready for sea. Forged Pelton runners are produced from high-grade stainless steel like ASTM 743 Ca6 NM. The process includes forging monoblocks, CNC machining, removing up to 70% material, non-destructive testing, precision welding, dynamic balancing, and hydraulic polishing. Final units are pressure tested and used in hydroplants with heads of 100 to 1,700 meters and outputs up to 300 megawatts. At Alpha ECC, head forming for pressure vessels involves hot forming steel plates up to 80 millimeters thick using a 1,000-ton hydraulic press after heating to 900 to 980 degrees Celsius. Post-forming heads undergo heat treatment at 580 to 650 degrees Celsius, then CNC machining to plus or minus 0.5 millimeters tolerance. Non-destructive testing, UTMPI, ensures integrity before final assembly and hydrostatic testing at 1.3 times design pressure up to 150 bars. Explosion bond cladding joins corrosion-resistant metals to strong base plates using controlled detonation. Plates up to 6,000 millimeters long are bonded without melting, then rolled, welded, and inspected. This method enables high-strength, corrosion-resistant pressure vessels, combining carbon steel with stainless steel, nickel alloys, or titanium, ideal for petrochemical and power industries requiring durable, cost-efficient components. The HAEU SLER VRM HY 4200-3730 is a powerful 4-roll plate bending machine designed for high-capacity forming in industries like shipbuilding, wind tower fabrication, and pressure vessel manufacturing. It can handle plates up to 30,790 millimeters long, 3,090 millimeters wide, and 250 millimeters thick, with a maximum plate weight of 75 tons. The machine weighs 600 tons, is powered by 700 kilowatts, and generates more than 8,000 tons of forming force. It features a linear side roll system and Bendtronic automation, allowing a single operator to control the full bending cycle with high accuracy. With the ability to pre-bend and roll in one operation, it minimizes material handling, boosts productivity, and forms complex cylindrical or conical parts with precision, making it a core asset in heavy manufacturing. SKF's Gothenburg factory in Sweden is a world-class production site specializing in self-aligning roller bearings. With over 1,250 employees and 33 advanced manufacturing channels, the factory produces approximately 1.2 million bearings annually across 4,100 variants, including spherical roller, thrust, and C-arb toroidal bearings, with outer diameters ranging from 130 mm to 2,500 mm. The production process integrates robotics, visual buffer systems, and lean manufacturing to ensure efficient flow and rapid detection of deviations. A major performance factor lies in SKF's proprietary two-step bainite heat treatment. which enhances steel hardness, improves consistency, and reduces ring ovality, leading to shorter grinding cycles and higher bearing reliability. Skilled personnel remain involved throughout the process, planning, controlling, executing, and continuously improving each stage. SKF's commitment to material quality, precision engineering, and automation ensures bearings that can endure extreme loads and misalignment in the most demanding industrial environments. Bruck produces high-precision gearings tailored to customer needs using 4 advanced gear milling machines. 2 main methods are applied. The down-cut hobbing method continuously rotates the workpiece, while a worm-shaped cutter mills the teeth, achieving top precision at quality level 9 for gears up to 7 meters in diameter and module 45, tooth size approximately 90 millimeter. The profile milling method machines each gap individually using carbide tools, allowing flexible angles, plus or minus 30 degrees, ideal for stacked gear production like wind turbine components. Bruck also performs internal gearing using specialized tools. Their carbide technology avoids oil coolants, making the process faster, cost-efficient, and environmentally friendly. The LASER TEC65 DID hybrid enables advanced additive manufacturing by combining laser deposition and milling in one machine. Using a 2 kW diode laser, it melts metallic powder through a coaxial nozzle with shielding and carrier gas. The directed energy deposition DED process is 10 times faster than traditional powder bed fusion, building wall thicknesses from 0.0039 to 0.2 inches. A complete turbine casing can be manufactured, with laser deposition taking 230 minutes, followed by 76 minutes of high-precision milling. For a fan wheel, deposition takes 312 minutes, and milling requires 240 minutes. Both wet and dry machining are supported. The hybrid CAD/CAM system, AM analyzer, and adaptive process control ensure precise geometry and surface quality. Complex 3D parts can be produced without support structures, reducing setup time and cost. This integrated approach streamlines production, delivering ready-to-use components with high dimensional accuracy and surface finish. The Wachen H6 horizontal machining center features a 630 mm pallet, handling parts up to U1050 mm and 1,600 kg. With XYZ travels of 1050/900 1,000ths of a millimeter and full 360 degrees B-axis rotation, it machines complex parts like SM45C herringbone gears. Powered by spindles up to 35 kilowatts and 1,654 Newton meters, it includes oil jet cooling, APC system, and up to 180 tool storage, ideal for high-precision, high-volume production. Mill-turn CNC machines, developed by WFL Mill-turn Technologies, are among the most advanced and versatile machine tools available for complete machining. Each mill-turn model is equipped with a main spindle and a counter spindle, both capable of delivering 29 kilowatts of continuous power and operating at speeds up to 5,000 revolutions per minute. The U250 mm chuck size on both spindles allows secure clamping of workpieces up to 1,500 mm in length and over 500 mm in diameter, depending on configuration. The counter spindle enables fully automatic part handover for backside operations, eliminating manual intervention and repositioning. A high-torque milling spindle is integrated into the system, enabling simultaneous 5-axis machining. It supports HSKT or Capto C6/C8 tooling and offers tool speeds up to 12,000 revolutions per minute, making it suitable for both roughing and high-speed finishing. This allows for complex operations, gear hobbing, cam profiling, multi-surface contouring, and internal pocket machining on one machine without reclamping. Milturn machines support large tool magazines with up to 200 tools, auto-indexed with a high-speed changer system in less than 5 seconds per change. Tool wear and breakage are monitored in real time. The entire machine operates under the Siemens Sinumeric 840 DSL or Heidenhain TNC 640, depending on customer preference, enabling integration with CAD/CAM systems, digital twins, and Industry 4.0 smart factory platforms. Precision is guaranteed through high-resolution linear glass scales and rotary encoders, achieving positional repeatability of plus or minus 0.001 mm. Built-in thermal compensation and vibration damping systems ensure dimensional stability, even during long cycle times and heavy material removal. Milturn machines are housed in rigid monoblock frames, with full chip management, high-pressure coolant systems up to 80 bars, and programmable tailstocks. These machines significantly reduce total production time by 30 to 60% by consolidating multiple processes, improving accuracy, and reducing workpiece handling. Whether producing turbine shafts, landing gear components, hydraulic cylinders, or powertrain housings, Milturn CNC machines offer unmatched flexibility, repeatability, and output capacity, supporting precision manufacturing from prototype to full-scale production.